Previously, we've discussed the chemical reactivity of the group 1 metals, lithium, sodium, potassium, rubidium. We talked about how they're great reducing agents, their electron configuration. We talked quite a bit about lithium and how it's used in medicinal applications to treat bipolar disorder. So we're going to continue on surveying the periodic table with the group 2 metals. But before we get into a lot of detail about the group 2 metals, we're going to start by reminding ourselves of this periodic trend of metallic character. And from that, we're going to talk about oxides. So both metallic oxides and nonmetal oxides, and whether they're basic or acidic. And then we're going to talk about the group 2 metals, their electron configuration, chemical reactivity, the reduction potentials, and we're going to specifically focus on beryllium and the uniqueness principle. And we'll also talk about beryllium with a diagonal effect and also give some focus on calcium. So we won't spend as much time talking about magnesium, strontium, radium, or barium. There's so much to talk about with each one of these elements that I've just picked out calcium because it's such a ubiquitous element, and also beryllium for the uniqueness principle. Okay, let's remind ourselves about this periodic trend of effective nuclear charge. I know we've talked about this so many times, but remember that your highest effective nuclear charges are in this upper right-hand corner of the periodic table, so fluorine, neon, helium. And remember that we talked about how as effective nuclear charge increases, our ionization energy increases. Remember that for something to be metallic character increases as ionization energy decreases. So another way of saying this is as our effective nuclear charge decreases, the metallic character increases. Metallic character is highest for this side of the periodic table, and we know for the opposite side of the periodic table, this is where our nonmetals exist. And then in here we have our metalloids, or things that have both metallic and non-metallic behavior. As effective nuclear charge increases, ionization energy increases, and metallic character decreases. And it's not binary. It's not, okay, you're a metal or you're a non-metal. There is this continuum or this range of how metallic an element is. So this is figure 8.21 from your textbook. And what it's showing is that as you move across period 3, going from sodium, magnesium, aluminum, all the way to chlorine. Sodium is the most metallic. Chlorine is the least metallic. It's a nonmetal. And silicon, for example, and aluminum, these two are both borderline. So they both have metallic characteristics and nonmetal characteristics. As you move down a group, such as group 5A, nitrogen and phosphorus, we classify as nonmetals. Arsenic and antimony are going to be borderline. So, and then once we get down to bismuth, we would consider this a metal. So metallic behavior increases going down a group and decreases going across a period. So we need to talk about oxides. Anytime you have a metal oxides form ionic oxides, which are basic. For example, sodium oxide plus water. If you dissolve sodium oxide in water, it forms hydroxide anions and sodium cations. So the pH will increase and the solution will be basic. Contrast that with nonmetals. Nonmetals form covalent oxides, which are acidic. Carbon dioxide is one that we talk about a lot with carbon emissions. When carbon dioxide dissolves in water, it forms carbonic acid. And carbonic acid is a weak acid that will decrease the pH of a solution. It's important to note that there are some elements that are on that metal-nonmetal line that have both nonmetal and metal characteristics that form amphoteric oxides. So their oxides can form as either an acid or a base in water. So just as a reminder, metal oxides are basic, and then non-metal oxides are acidic. So just as an example, we're talking about group 2 metals today. So a basic oxide is calcium oxide. Calcium oxide in the presence of water dissolves to form oxide, O2 minus. Oxide is very reactive and will react with water to form 2 hydroxide anions. Contrast that with P4O10. So this is an oxide of phosphorus. When it reacts with water, what happens is it forms phosphoric acid, which we know is a weak acid that can dissociate to form hydronium ions and the conjugate base. So if you were to dissolve each one of these oxides in water with an indicator, you would see that calcium oxide is basic and this oxide of phosphorus is acidic. The acid-base behavior follows the metallic character trend. So elements become more metallic as we go from right to left, and they also become more basic. Aluminum is borderline. Non-metals are forming acids, and the strength of the acid increases the less the metallic character. So N2O5, it also has to do with oxidation state as well, not just whether it's a metal or a non-metal. And sulfur trioxide, for example, will form sulfuric acid. Here's a few examples. Carbon dioxide and water forming carbonic acid, sulfur trioxide and water forming sulfuric acid, and nitrogen dioxide and water forming nitric acid. So these you can think about. This is important because all of these are pollutants. So carbon dioxide is a pollutant from burning all different types of fuel. Sulfur trioxide is a pollutant when we burn coal, and nitrogen or NOx pollution is a pollutant that we burn when we burn gasoline. And so when all of these get into the atmosphere and react with water, they form these different acids. So these are all of these non-metal oxides are examples of pollutants that contribute to acid rain. Okay, so let's talk about the group 2 metals. So you'll notice that they all have this noble gas NS2 electron configuration, where N is the period number. So they're good reducing agents, but they don't have as negative of a reduction potential as the group 1 metals. They have a very similar reaction to the group 1 metals. When the group 2 metals react with water, they again reduce the hydrogen in water to form hydrogen gas and form the basic calcium hydroxide. So again, this is why they're called alkaline earth metals, because they increase the pH. Let's talk about the uniqueness principle of beryllium. So remember, our elements in period 2 are uniquely different from the other elements in the group, and beryllium is no exception. Beryllium is exceptionally small, and beryllium 2+ has an exceptionally high charge density, and because of that, it has a really high polarizing power. So beryllium 2+ doesn't form ionic compounds. It actually forms compounds that have covalent character, like beryllium chloride. So this is not, most of the group 2 metals form ionic compounds, but beryllium will often form these covalent compounds. This example of BeCl2 is an electron deficient compound. It does not have a full octet, but solid beryllium chloride looks a little bit different, and there's a full octet around beryllium. I also wanted to mention beryl. Beryl is a gemstone with the formula Be3Al2Si6O18. So it's a mineral, and you might also know beryl under the names of morganite, aquamarine, and emerald. This particular mineral, we call it different names depending upon the impurity. So morganite is a popular gemstone, and it is beryl that has trace manganese 2+. Aquamarine is beryl with trace iron 2+, and emerald is beryl with trace chromium 3+. We already know about transition metals and how they cause color, either through D to D transitions or through charge transfer events. So pure beryl is colorless, and the defects are what create the color in these different minerals. So again, either by D to D transitions or charge transfer. We also need to talk about the diagonal effect again with beryllium. So remember that there's this diagonal relationship specifically between beryllium and aluminum. And this is again because they have similar charge to size ratios, similar electronegativity, similar charge density. You can see this here. Beryllium is very small. Its ionic radius is only 0.41 angstroms, has a charge of +2. The charge density is very similar between beryllium and aluminum, and they have almost identical electronegativities. And so because of that, they have some similarities. So here's some of the similarities. Both form oxoanions, so berylate and aluminate. They both form these bridging bonds in their hydrides and their chlorides. So we talked about these similar structures of BeCl2 and aluminum chloride when we introduced the diagonal effect. They also have similarities in their oxides. Remember, we were just talking about acidic and basic oxides. For both beryllium and aluminum, the oxides are amphoteric and the coatings are impervious to water. We also mentioned that beryllium forms covalent compounds. And aluminum also can form compounds that have significant covalent character. And this, again, is due to this high charge to size ratio, making both aluminum 3+ and beryllium 2+ able to polarize electron clouds very easily. Okay, let's also talk about calcium. Calcium is incredibly ubiquitous. There's so many different ways that we encounter calcium. Anytime you have an upset stomach and you take some Tums, that's calcium carbonate. A lot of different limestone structures. Limestone is calcium carbonate. So there's a lot of different ways that we see calcium carbonate. Eggshells, seashells, so many different ways that we encounter calcium carbonate. So the first is limestone. Limestone is calcium carbonate and is a type of calcium carbonate. And it's very common in architecture. So pyramids, the York Minster, all of these are made from limestone. One of the issues with calcium carbonate is that carbonate is a base. Calcium carbonate is insoluble, but when an acid is present, the equilibrium is shifted towards calcium dissolving. So if carbonate reacts with an acid to form bicarbonate, then this is going to shift the equilibrium to the calcium carbonate dissolving. This is just based on Le Chatelier's principle. Calcium carbonate is used as Tums because, again, carbonate's a base, so it can neutralize your stomach acid. So calcium carbonate will react with the hydrochloric acid in your stomach to form calcium chloride, carbon dioxide, and water. Another example of calcium carbonate are frescoes. So two of the most famous frescoes that you're probably familiar with are the Sistine Chapel, and also the Esse Homo that is in Spain. And this fresco was in the news a lot over the last few years because a very well-meaning woman that was not trained on how to restore frescoes tried to restore this particular fresco, and she didn't do it correctly. And so a lot of people were talking about this fresco. Okay, so the way that a fresco works is that calcium carbonate is limestone. So we have this quarried limestone and we heat up the limestone. So this delta is representing heat to release the carbon dioxide and form quicklime or calcium oxide. Water is then added to the calcium oxide to form calcium hydroxide, or it's called slaked lime. And this slaked lime is like plaster. And what a painter would do is it would apply this slaked lime onto a surface and then paint with pigments directly onto the wet lime putty or plaster. You can think of it like a plaster. And then what would take place is as the fresco dried, water is released and then carbon dioxide from the atmosphere is absorbed and calcium carbonate is again formed, but now the pigment is incorporated. So this is an example of a fresco that my student Dana made back in fall of 2016. And what took place here is she took a piece of tile, then she applied the calcium hydroxide onto the tile, So this was the calcium hydroxide, the slaked lime. And it was sort of wet, so you could spread it out. It was a putty. And then what she did, and what all of the students did, was then they took pigments and painted directly onto the slaked lime. So you could just take literally a pigment in some water and paint directly onto the putty. This is acting as a binder. So when you want to paint something onto a surface, you need a way for that pigment to stick to the surface. And so by painting directly onto the plaster and incorporating the pigment directly onto the plaster, it creates a really nice permanent painting. Okay, another way that you've probably heard of calcium used is the term limelight. We just mentioned that lime is another name for calcium oxide. So specifically, quicklime is calcium oxide and slaked lime is calcium hydroxide. Lime is calcium oxide. When you heat up any material to a really high temperature, it will give off light in the form of black body radiation. That's how a light bulb works, a traditional tungsten light bulb. But calcium hydroxide is unique in that it can be heated to incredibly high temperatures. Its melting point is over 3,000 Kelvin. And so you can heat calcium oxide to very high temperatures to cause it to give off a very bright light. So you've probably heard the term limelight. So what limelight is it's a piece of calcium or a large amount of calcium oxide. It's some calcium oxide that's being heated, and once it's heated to a very high temperature, it gives off white light. We already mentioned that calcium oxide can be formed by heating limestone. So calcium carbonate, heating it up to form calcium oxide and carbon dioxide. And the calcium oxide is heated with a mixture of oxygen and hydrogen gas on fire, and that's what creates these original spotlights. So the bright light was then focused using curved mirrors and was used as a spotlight. So that's where the term "in the limelight" comes from. In the limelight comes from calcium oxide being used as a spotlight. Okay, so there is a lot about the group 2A metals that we are not going to get to, unfortunately, but a few reminders. They're great reducing agents. Calcium, especially calcium carbonate, is ubiquitous, but we also see calcium as calcium oxide or calcium hydroxide. And beryllium is unique. It's the only 2A metal that forms covalent compounds, and we also looked at some of the beryl gemstones such as emerald, morganite, and aquamarine.